Hi guys, this is organic chemistry and we're looking at types of bond breaking. Heterolytic fission or heterolysis refers to a bond that is broken in such a way that one of the two species forming the bond retains both the bonding electrons and the other species loses its bonding electron. So heterolytic fission also means different breaking of bond. So let's take the example of a molecule A and B, which is covalently bonded. Now, between these two, A is less electronegative and B is more electronegative. So, when this compound undergoes heterolysis, the bond will break in such a way that A loses its bonding electron and becomes positively charged, and B retains both the bonding electrons as seen here and becomes negatively charged. So we can call A positive a cation and B negative an anion. But that is not how these ions are referred to in organic chemistry. So what has happened is A has lost its bonding electron and became electron deficient. So A is electron deficient because it has lost its bonding electron, and B has gained an electron and has become negatively charged. So an electron deficient species and a negatively charged or an electron rich species, let's call it electron rich, have been produced. Now the electron deficient species in organic chemistry is called an electrophile, and an electron rich species in organic chemistry is referred to as a nucleophile. So an electrophile can be translated as being electron loving or having affinity for electrons, and nucleophile can be translated as nucleus loving or has affinity for the nucleus because nucleus is positively charged. So nucleus having can also be positive charge loving. Phile stands for loving or affinity towards. So we will not use the term cation or anion in organic chemistry. We will use the terms electrophile and nucleophile to represent a positively charged species and a negatively charged species. However, an a nucleophile need not have a negative charge because a nucleophile should be electron rich. It does not mean that it should have a negative charge as well. So, for a nucleophile, the negative charge is not required. Negative charge is not required. A nucleophile must have a lone pair of electrons present, and that is how you can classify a molecule also as a nucleophile. For example, in order to classify nucleophiles, we can have a Cl negative ion because it will have lone pairs of electrons. We can have an OH negative ion because it will have lone pairs of electrons. We can have a Cn negative ion because it will also have a lone pair of electron like this. However, a water molecule is also a nucleophile because the oxygen atom on water has lone pair of electrons. Also, an ammonia molecule acts as a nucleophile because the nitrogen atom has a lone pair of electrons. So, this is proof that nucleophiles need not carry a negative charge but must always have a lone pair of electrons present in order to be classified as nucleophile. Another thing that needs to be understood about heterolytic fission is that if we have a compound, for example, CH3Cl undergoing heterolytic fission. So CH3Cl, the bond breaking is the CCl bond. So we can write it as CH3 and Cl. So when this undergoes heterolysis, the bond breaks in such a way that CH3 loses its bonding electron, or rather, carbon loses its bonding electron and becomes positively charged, and the Cl gains the bonding electron and becomes negatively charged. So the CH3 positive becomes the electrophile, and Cl negative becomes the nucleophile. Now, this is organic chemistry. Organic chemistry is based on the chemistry of carbon. So, carbon has a very important position. So, here the positive charge on the CH3 plus ion is on the carbon atom. So, the electrophile itself will have a special name in this case. That is, in any case, if you have a positive charge present on the carbon atom, the positively charged species would be referred to as a carbocation and this is because of the special position carbon holds in organic chemistry. So, if the electrophile formed is a carbon containing species with the positive charge present on the carbon atom, it will be referred to as a carbocation, and this needs to be remembered. The positive charge on the carbon atom forms an electrophile that is called a carbocation. Now we are going to look at homolytic fission or homolysis. Homolytic fission meaning same breaking of bond. Now, same breaking of bond is brought about by UV light. If we have a molecule like Cl2, in which both the bonding electrons are present between two atoms in which there is no electronegativity difference. So what happens is the UV rays, they make this bond vibrate in such a way that the bond shatters. This is just like sound wave shattering a glass. So the bond is not overcome by providing sufficient energy known as bond energy. In fact, the UV light vibrates the bond in such a way that it shatters, resulting in the formation of two species that are exactly the same. These two species each retain one of the bonding electrons, but the bonding electron was not given enough energy to break free from the bond itself. In fact, the bond shattered and the two species formed are referred to as free radicals. Now, free radicals are highly reactive species. Whenever they are formed, they attack any molecule close to them and reform their own bond while creating another free radical of that particular molecule. So, free radicals, when formed, undergo free radical substitution reaction mechanism. Free radical substitution reaction mechanism. Now, these free radicals that are formed are made of chlorine, so they are known as chloride free radicals. These are chloride free radicals. So, when we are talking about the free radical substitution reaction mechanism, we start with a molecule of chlorine, and this is how the reaction begins or initiates. So, we are looking at the mechanism of free radical substitution. So, the mechanism involves the initiation step, which is the exact same step as already seen, in which we have Cl2 undergoing homolytic fission in the presence of UV light, producing chloride free radicals. Now, these chloride free radicals are going to attack the molecule that is present in them. So, what we are going to do is we are going to have this reaction take place in the presence of methane, which will be methane plus chlorine gas in a container when exposed to UV light. So, the initiation step has already been discussed, in which the two chlorine molecule, rather the two chlorine atoms in the chlorine molecule are affected by the UV light, the bond is shattered, and we have production of two chloride free radicals. As the reaction continues, the next steps are known as the propagation steps, in which we have a methane molecule CH4, which is attacked by a chloride radical. When it is attacked by a chloride radical, the chloride radical forms a bond with one of the hydrogen atoms, breaking the CH bond, forming a CH3 radical, and itself being converted into HCl. So the CH3 radical that is formed is now known as the methyl free radical. In the container this is formed in, we have got more chlorine molecules. So this methyl free radical attacks a chlorine molecule and breaks it homolytically, converting into CH3Cl. Now CH3Cl is basically chloromethane, and when the Cl2 bond breaks, a chloride free radical is formed. Now this chloride free radical may attack any molecule present in the container, which includes CH3Cl itself. So if it attacks CH3Cl, so what it does is it takes away one hydrogen atom, producing CH2Cl radical, and itself being converted into HCl. So as you can see, this is a chain reaction taking place, each step producing a new radical, that radical attacking a molecule, producing another radical, and itself being converted into a molecule. So the new radical produced is called chloromethyl free radical. In this way, the reaction will continue until all the hydrogen atoms in methane are replaced by chlorine atoms. So we can actually write that the chain reaction continues until all of the hydrogen atoms in CH4 are replaced by chlorine atoms, and the final product CCl4 forms. So now that the final product is formed, now it depends on which compound was in excess, whether it was methane or it was chlorine. We get to experience termination steps so that the reaction ends, because it's a chain reaction, it needs to end. So termination. So termination involves possibility of three reactions. The first one is, if chlorine was in excess, then two chloride free radicals will collide with one another, reforming the chlorine molecule. If methane and chlorine was in equal quantity, so we would end up with a methyl radical colliding with a chloride free radical, producing CH3Cl. Or if methane was in excess, so we might end up with two methyl free radicals colliding with each other, producing ethane. Now, this is something that was not present in the container when the reaction started. So, this also brings us to another point that needs to be noted, that the final product is CCl4. However, there are other possible products that can also form. So, the major product is CCl4, but there are minor products that also form, which include CH3Cl, CH2Cl2, and CHCl3. Now, these are all the products that contain one carbon atom. We have formation of ethane in the termination step. So, there are some minor products with two carbon atoms. Minor products with two carbon atoms. Now, this depends on which radicals are present. So, the radicals that are present, free radicals. So, the free radicals present are CH3 dot, then we have CH2Cl dot, then we've got CHCl2 dot, and we've got CCl3 dot. So if we label these radicals as 1, 2, 3, and 4. Now, since we are going to make a lot of other minor products, so instead of making the product completely, I'm going to put them together in the form of the numbers that have been labeled to these radicals. So one of the products will be 1 and 1. 1 and 1 would mean both of them are methyl free radicals. We can have 1, 2, we can have 1, 3, and we can have 1, 4. These are the four possible products with two carbon atoms present. Then we can have 2, 2, 2, 3, and 2, 4. These are the three more additional products that can form when either of these four radicals during the chain reaction collide with one another. These are just possibilities. It is not that all of them will form. It is just that some of them will form, but these are all the probabilities that can happen during this reaction. So moving on, we can have 3, 3 and 3, 4 forming. And finally, we can also have a molecule of 4 and 4, yeah, which means both carbon atoms containing 3 chlorine atoms. So in total, C2Cl6 will form when 4 and 4, the radical labeled 4, combines with another radical that is labeled 4. So in total, if we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 minor products containing 2 carbon atoms are also possible during this reaction. However, the major product of the reaction stays CCl4, in which all four hydrogen atoms of methane have been replaced by chlor chloride free radicals, and the molecule CCl4 tetrachloromethane formed.